In this next example problem, we have a kid that is swinging a rock around in a circular loop. The rock is traveling roughly parallel with the ground, so a side view would look something like this. Now you know that if you tie an object to a string and you swing it faster and faster, at some point that string is going to break. And we're told that if the tension in the string exceeds 1,000 newtons, then the string will break and the rock will just go flying off in a random direction. So we are asked, what is the fastest possible speed the rock could move with the string just barely not breaking? Now, a side view would look something like this, but let's draw an overhead view of this scenario. So my overhead view, I have the path that the rock travels when it's swinging around its loop. Let's draw the rock to be right here at this moment. So the velocity of the rock will look something like this. And the radius of this loop is going to be 3 meters because the string has a length of 3 meters. We are told that the rock is moving at a constant speed. And we know that if an object is moving in a circular path at constant speed, the direction of that object's acceleration is inward towards the center of the circle. So I'm going to draw that acceleration on this picture. Constant speed, circular path, acceleration is inward towards the center of the circle. Now let's think about the forces acting on the rock. There is a string tied to the rock, and therefore there will be a tension force acting on the rock. The string is what causes the rock to move in this circular path. You could imagine that at some moment, if you were to cut the string, the rock would just continue moving in this direction. It would no longer be moving in a circular path. So there is a tension force acting on the rock that is pulling the rock towards the center of the circle. There are no other forces to be drawn in this picture, so I could begin setting up Newton's second law. So if I write F net equals ma, I could write the tension force in this problem is equal to the mass of the rock times the acceleration of the rock. There is only one force acting on the rock that's important in this picture, and that's the tension force. So, the tension force, we want the string to be barely on the verge of not breaking. So let's make the tension force as big as possible. So we'll set the tension force to be equal to 1,000 newtons. Now, the acceleration of the rock will have a magnitude v squared over r. We said that anytime an object moves in a circle at constant speed, the acceleration is going to be v squared over r. So I could write the tension force of 1,000 newtons is equal to the mass of the rock times v squared over the radius of the loop that the rock is traveling around. So that would be 3 meters. And if I put these numbers in a calculator, I get 1,500 is equal to v squared. So I get the speed of the rock is going to be 38.7 meters per second. So this is the fastest I could swing the rock where the string is barely not breaking. If I swing the rock at 38.8 meters per second, then the string breaks. Now, at this point, we are completely done with this problem. But you might be asking, we set up Newton's second law. What about gravity? Why did we not account for gravity? And first of all, I did say very briefly that the tension force is in the same direction as the acceleration in this picture, so the tension force will be entirely responsible for the acceleration. Gravity is perpendicular to the tension force in this problem. Gravity is perpendicular to the acceleration, so we didn't really count it. But shouldn't we be accounting for gravity? Where is gravity in this problem? So let's draw the forces acting on the rock in this picture up here. And let's see if we could learn about what's really going on in this scenario. So I could say there is a force of gravity pulling the rock straight down. I'll call that F gravity. And again, we have our tension force like before. So I have a tension force pulling this way, F tension. Now, we said the acceleration of the rock is inward towards the center of the circle. So here's the acceleration of the rock. And at this point, if you want, pause the video, think about what's going on in this problem. And specifically, ask yourself, is this a realistic scenario? Is this scenario possible? And the answer to that is, strictly speaking, for an instructive example, this scenario could be useful, but in the real world, this scenario is not possible. It is not possible to swing an object around in a loop and have that loop be perfectly horizontal. The rope will always have some slight downward angle in it due to the force of gravity. So in this case, you would have to swing an object around at an infinite speed to have this loop be perfectly horizontal. In a real scenario, we would have to have this loop be, the string would be at a slight angle. So in a real scenario, you would have the kid swinging the rope, and the string would look something like this as the rock travels around its loop. And now if I draw the forces acting on the rock, I have a downward force of gravity. This would be partially canceled by the partially upward force of tension. The vertical component of the tension force will cancel the vertical component of gravity, and that's why the rock is not accelerating up or down. And the horizontal component of the tension force will be this inward force that produces this centripetal acceleration. So strictly speaking, an object being swung around by a string, that string can never be perfectly horizontal. That string will always have a bit of a dip, a bit of an angle to it, and that's because gravity still exists. You would have to swing the string around at an infinite speed to get rid of that angle completely. You can make it very small though if you want, depending on how fast you want to swing it. A second and final thing I want to mention about this problem. You will see the idea of centripetal acceleration, and you will see the idea of centripetal force in this course a couple times. And I want to say that, in a way, centripetal force is not actually a thing. Tension is an example of a force. Gravity is an example of a force. There's no such thing as a centripetal force per se. So if I have an object that is moving around in a circular path, I know that object is going to be accelerating in towards the center of the loop. We are assuming that it's moving at constant speed. And you could ask the question, what is the force causing this acceleration? Now, if the string is the object tied to the rock and the string provides a tension force, I could say there is a force of tension producing this centripetal acceleration. But on the other hand, if you imagine a planet orbiting a star, and let's say that planet orbits in a circular orbit, then you could say the force of gravity from the star acting on the planet will cause that planet to undergo this centripetal acceleration. So in the first case, I could say the string acts as a centripetal force. In the second case, I could say gravity acts as a centripetal force. Tension is a type of force. Gravity is a type of force. Centripetal force is not a type of force. The centripetal force is just whatever force happens to produce this centripetal acceleration.